We're going to go ahead and take a look at the test for the difference in proportions, which before we really get to that, we have to deal with what's referred to as a pooled proportion before we get to the difference or test of difference in proportions. So if you've not done so, pause this video, watch this YouTube video on split or steal, with which is a video about the golden balls. It's a game show. This link should be in your notes, so go ahead and watch that if you've not done so. So, for the most part, if both choose split, the jackpot is split. If both choose steal, nobody gets anything. If one says steal and one says split, the stealer gets everything. So what should you do? Should you split or should you steal? So the game show's been going on for a while, and here's the data of what's been happening, whether they're splitting or stealing, broken down by gender. So are males or females more cooperative? So we're going to use P subscript M for our proportion of males who split, and then P sub F for the proportion of females who split. So let's calculate the difference in our two proportions. So we'd have to take the males who split over the total number of males, and that's what we have here. Then we got to take the females who split over the total number of females, and that's what we have here. And we got to just subtract those two. So this first fraction goes down to this decimal, second fraction to this decimal. When you subtract those two, you get negative 0.014. So when we're looking at our hypothesis testing, we want a distribution of our sampling proportion, assuming the null hypothesis is true. Well, we have our null hypothesis being true here. In other words, the two proportions are equal. And then we have our standard error that we've looked at before. But what do we use for P1 and P2 so that we can say they're being equal? Well, to do that, we need to go ahead and work with one proportion where, for the most part, it would be our proportion of our best guess that these would be two equal. So what do? We take our two groups and combine them into one. In other words, we get the pooled proportion, the overall proportion of our two individual ones. And your pooled proportion will always be between your two individual sample proportions. So, how do we find our pooled proportion? We need to take the total number of males who split, add the total number of females who split, over the total number of males who played the game, plus the total number of females who played the game. So we take the males who split, plus the females who split over total males and total females. Add the top, we get 303. Add the bottom, we get 574. And then we divide. That's our pooled proportion. So the difference in proportions, our test, this is our basic formula for test, our statistic minus our null over our standard error. So we're going to go the difference in our two proportions. And then we're going to use our pooled proportion times 1 minus our pooled proportion over the sample size of the males for this case. Pooled proportion minus pooled proportion over the sample size of the females, all inside of a square root for our standard error. Now keep in mind that your sample size times p hat has to be greater than 1, and sample size times p hat has to be greater than 10 for both sample sizes. We had talked about the conditions of that before with the central limit theorem in the last video. So, based on this data, can we conclude whether males or females are significantly more cooperative in playing golden balls? So we're going to first of all start off with our parameters and defining our parameters and then setting up our hypotheses. Our null hypothesis is always that they're equal. Our alternative, we're just wondering if there's a difference. So then you want to make sure there's 10 or more in each category, which there was. So we can check that off. We dealt with that. So we figure out that pooled proportion, which we already did, but it's just here on this screen. Then we got to go ahead and use that in this formula. So P sub 1 with the hat is our proportion of our males. P sub 2 with our hat is a proportion of females. P with the hat is that pooled proportion that we had right here. So we got to go pooled proportion times 1 minus pooled proportion. That's what we have right here over the sample size of our males. And then pooled proportion times 1 minus pooled proportion over the sample size of the females. So if we work out the top, we get this here, and that's what we did when we looked at the difference in our two proportions. And then the bottom is the standard error. So go ahead and type all that in. You get 0.042. When you divide these two, we get a z statistic of negative 0.33. So then we go to stat key, and we pull that up underneath our normal distribution because we're dealing with the z. And we click two tail, and then we click on the bottom and enter 0.33 on the right one, and that's going to then give us our p-value. Now our p-value, because it's a not equal to, is going to be the area of the red on the right plus the area of the red on the left, or you can take one of the areas and just multiply it by 2, and that's what we get. So we get a p-value of 0.74. So based on this data, we cannot conclude anything about males and females being more cooperative because this p-value is significantly larger than a typical 0.05 confidence or significance level. Now, what's more interesting is this, that there's a difference in males and females at the younger ages, but that difference is kind of reversed for the older ages. Notice how at the younger ages, females are higher, males are lower, but at older ages, males are higher, females are lower.